There are many right answers to this problem, and so I'm going to talk about my analysis, my take on what the different schools of thought are about how you could fix things. So I think there's roughly 4 approaches. There might be more, but these are the ones I thought of. The first is to rely on randomness, and in that way, we will avoid issues with bad ordering by ignoring the original ordering. I'll talk more about that in the next slide. We could try and do something where we pick a smarter pivot than the leftmost pivot, where instead of using randomness, we actually pick the best possible pivot. So we know, if you think very carefully about it, the best possible pivot would be the median. That's the item that's going to land in the middle. So if we can identify the median, well, then we know the right pivot. Third, we could do some kind of introspection. So we have a version of QuickSort that runs, and it tracks its own recursion depth. And if it finds that that recursion depth is too big, it switches to some other sort. And then the fourth approach, which seems to be the most popular with students, is we could look at the array and see, is it bad? And if it's bad, well, don't use QuickSort. So that obviously raises the additional question, what constitutes a bad array? And so you might say, well, we check if it's sorted. But it's not enough just to check if it's sorted, because if it's almost sorted, or if it's an array of almost all duplicates, well, which means it'll be almost sorted, then QuickSort's still bad. So we need some other more complicated preprocessing strategy other than just checking if it's sorted. We don't have such a strategy. That's an interesting question. You can develop this further, and actually I think I'm going to add it to the study guide questions, but this approach just isn't done in the real world, and it has to do with the fact that detecting in advance that an array is bad is actually quite challenging. So I'm going to focus on these first 3 strategies. The first strategy, which is my favorite approach, is to use randomness. So recall the issue was that things go wrong if we keep getting really unlucky with where our pivot moves, if it just stays in the same place, for example, or doesn't move very far. Now, the issue is that while it is extremely unlikely if you give in a random array that you'll get this worst case, in real situations, as we saw, we have bad ordering and bad elements. These 2 cases can actually cause us problems. So we can avoid the bad ordering issue if we just use some kind of randomness. So for example, if we pick the pivots randomly, that is, then it doesn't matter what order the array was originally in, because we're picking the pivot randomly. And so in this case, we're effectively doing random BST insertion, right, by picking pivots randomly. The alternate strategy is just shuffle before you sort and still use the leftmost element. And these 2 strategies are very similar to each other. Now, this second strategy, while it's the approach used in our optional algorithms textbook, it has one little caveat, which is you need to be very careful about how you handle arrays of duplicates. So if your partitioning strategy doesn't make sure that let's say you have an array of all duplicates, if that array of all duplicates keeps the pivot at the leftmost position, then you can end up with n² runtime. Now, it's a little more detailed than I really want to go to in lecture, but it will be a study guide question if you're curious about this. Okay. Now, the point here is just, to summarize this whole slide, if you pick your pivot randomly, your QuickSort is going to be n log n with incredibly high probability. If you pick shuffling before you sort, well, it's still going to be n log n with incredibly high probability, so long as you're careful about how you handle duplicates in your partitioning algorithm. So this version of QuickSort, I like it. I think it's really lovely. You throw a dart, and you know that it's extremely likely that you're going to bullseye. There's a tiny, tiny chance that, it's like, unfathomably unlikely. Yeah, technically it could go awry, but with just a tiny change to our algorithm, just picking the pivot randomly, boom, now we got a good QuickSort. And so I always think about this version of QuickSort as like this guy. This is from a TV show, which I've never seen, by the way, called Renegade. But hey, look at this guy. He's got this long, crazy hair. He rides a motorcycle with some kind of almost rainbow on it. This is a guy who doesn't play by your rules. He does whatever he wants. He gets the job done, but he's a little reckless, out of control. Okay, that's this version of QuickSort. So I think pretty fun from an aesthetic point of view. I think it's just a really interesting way of approaching the problem of sorting. Scrambling in the process of sorting, it's cool. All right, order from chaos. It's fun. Now, maybe you're not that way. Maybe you don't like this approach of being random. Maybe it seems dirty that a sort should involve randomness. Well, there's a solution for you, and that is trying to do smarter pivot selection. And so this is what's done, for example, in Java. In Java, what they do is they look at some number of elements and they figure out what is the median of that subset of elements. So you pick, I don't know, well, one common strategy is take the first 3 elements in your array, use the median of those 3, and have that be the pivot, right? And there's other versions that involve looking across the array, long distances. There's a bajillion different versions of this, okay? Now, this approach has one major issue. You can show that if you have a pivot selection algorithm that is deterministic, so it has no randomness, and second, that it's constant time, that is, it only looks at a constant number of elements, then there exists a sequence of values that will cause your quicksort to go n squared, and it can be computed. So there's a paper here that I think's really, it's like an hour and a half maybe to figure out what it's saying, but it explains, given a version of quicksort with these properties, you could generate an array. And actually that's true in Java. There exists an array in Java of numbers that you give to the built-in Java quicksort, and it will cause it to go n squared and ultimately crash because it runs out of stack memory, I think it is. I think that's what happens. I'm pretty sure. Yeah, it causes a stack overflow if you feed the actual official Java quicksort some totally arbitrary array. And if you're curious, I don't know, email me and I'll make a video about it. It's pretty fun. Okay. So this approach, while elegant, it has an Achilles heel, that there's some dangerous input that will cause the quicksort to break, and that input can actually be generated and maybe given to you by an adversary. Now there's a way around that, which is philosophy 2b, which is let's actually find the exact median. So rather than saying, okay, well, let's approximate the median, let's find the exact median. But the problem with this is that while it is worst case n log n, this overall approach is slow. And we'll see that in the next lecture, the next video that comes for tomorrow's lecture. Okay. Now this raises the interesting question of how do you compute the median of an array? And I'll be talking about that, as I noted, in the next lecture. How do you get the median, and what are the consequences? That'll be for later. So maybe you like this approach better. Slower, but safer than this guy. All right, and then the third approach, which isn't done super often in practice, but it's a perfectly reasonable approach, is just simply watch your recursion depth. If you find that your quicksort is, 10 natural log n, well, things are weird. It shouldn't be that much, so let's switch to merge sort. Then you incur some kind of a cost, sure, by having to switch over, but it's extremely unlikely. And so that's an approach that happens sometimes. Okay. Now the problem with this is if you are very often sorting arrays which are almost sorted, you're wasting a lot of time just doing extra quicksort results that you're just going to throw away. So I think the first 2 philosophies are better, and especially philosophy 1, as I mentioned, which is my favorite. Okay, so to summarize everything we got so far. This lecture, we have developed the new type of sorting, which is based on partitioning. It's a new, totally different way of thinking about sorting. It has a theta n log n expected runtime and a theta log n expected memory, and that's because the depth of the recursive calls is theta log n expected. Though in the worst case, it could be theta n. In the worst case, time for quicksort could be theta n squared. Now, despite those slightly messy runtimes there that they're expected, messy performance characteristics that they're expected, this is still, on average, the fastest sort. So in the next lecture, we'll actually do some speed testing, and we will compare the performance of different flavors of quicksort to merge sort. And so stay tuned and check that out. All right, see you next time.